Hello friends, today we are going to start our third lecture of vector analysis. Our topic is here we will be discuss about how to find unit vector, next vector addition, and the third topic is properties of the vector addition. My name is Majid Ali. Let's start our video on solving the examples that how to find a unit vector of a given vector. First we look some concept about the unit vector. In the previous video we defined the unit vector that a vector whose magnitude is 1. In this video we will be discuss only some example of finding the unit vector. In the previous lecture we discussed about the unit vector. After review we will come to know that how to find the unit vector of a given vector. So we start from the mathematical explanation of a unit vector. Here is we know that a unit vector is equal to a vector hat is equal to a unit vector divided by its magnitude. Here in Cartesian coordinate system the unit vector can be defined by an equation 1. This is a hat, which is also called the unit vector of a, which is equal to xi plus yj plus zk. Xi, yj, zk is the component of a vector along x-axis, y-axis and z-axis. Here is the magnitude, square root of x square plus y square plus z square. Now we have find the unit vector of given vectors. Here is some examples. Example number 1. First find the magnitude of each vector and find the unit vector of given vectors. First we will be find the magnitude of both vectors, then we will find the unit vector. Here is the magnitude of first vector, that x coefficient of I component square plus coefficient of y component square plus coefficient of k component square. This means x square y square and z square, which is equal to 1 plus 1 plus 9 is equal to square root 11. And the magnitude of vector b similar, x component I unit vector square and coefficient of j unit vector square and coefficient of k unit vector square, which is equal to 3 square 1 square and minus 1 square, which is equal to which is equal to square root 11. By substituting the values of both magnitude in equation 1 that we will see in the previous slide, you can see by reversing the video that the formula is a unit vector is equal to vector given vector over magnitude of the given vector. This is the given vector a, and here we find magnitude of a, and similar we find the vector b, unit vector b. This is the vector b, given vector b and its magnitude in the denominator. Next, here is the example 2. Find the unit vector in the direction of vector a is equal to 2i unit vector plus 2j unit vector minus k unit vector. The solution is similar, that we have a unit vector u which is equal to vector u divided by its magnitude. First we will find the magnitude by the same formula, that square of I coefficient of I unit vector, which is 2, and square of coefficient of j unit vector, which is also 2, and square of coefficient of k unit vector, which is minus 1, and 4 plus 4 plus 1, which is equal to 9. 9 square root is equal to 3. Substituting the values in equation 1, that we have a formula that vector a unit vector of u, which is equal to vector u divided by its magnitude. This is our second topic, which is the vector addition. We add the vectors by both like geometrically and analytically. First, by geometrically we can add vector by head to tail rule. Analytically we use usual simple algebraic expressions. Here is the head to tail rule, which is stated as two or more vectors are added as the terminal point, which means head of the first vector coincides with the terminal point tail of the next vector. Here is not the terminal vector, here terminal point, here is the initial point. Tail is the initial point of second vector, terminal point of the first vector, and initial point of the first vector of the next vector, and the resultant vector is obtained by coinciding the tail of the first vector and head of the last vector. Here is a little bit mistake that here come the initial point, which is the tail, as we have been seen in the first lecture. Now let's have a look on geometrical representation of addition of vector. Let this is vector A, which have a direction and sense. This is vector B, vector C, and vector D. We will be added all of the vector one by one geometrically by using head to tail rule. Here is vector A. We add the vector B, as you can see there that the head of the vector A coincide the tail of the vector B. Both are meeting at the point. This is the rule of head to tail rule, and the resultant is a vector that is drawn from tail of vector A and head of vector B, just like this. That the resultant vector coinciding the tail of first vector and head of last vector, that tail to tail and head to head. This is the resultant vector A plus B. Now we will add A, B and C. This is vector A, vector B and vector C. As you are seeing that the head of first vector coincide the tail of second vector. This is the head to tail rule, that head and tail. And in the case of B and C, the head of vector B coincide the tail of vector C. And this is the resultant vector, that the resultant vector from tail of the first vector and head of the last vector, which is the C, and resultant vector is analytically R is equal to A plus B plus C. This is the analytical representation of the vector addition. Now we will add four vectors, vector A, vector B and vector C, as you have seen in this case. And here is the vector D, that tail of the vector D coincide the head of vector C, and the resultant vector is the tail of vector A coinciding the tail of A and head of D, which is the resultant vector of A vector plus B vector plus C vector plus D vector, and similarly we can add more than four vectors. This is the law of polygon. Now we will see the vector subtraction, that it is also the take place by using the head to tail rule. But in subtraction we require the negative vector that get from the given vector by changing its direction in opposite side. This is vector A and this is vector B, and if we added two vectors, then this is the addition of vector, but we need to subtract vector. That's why we required a negative vector of B, which have the same magnitude and opposite in direction, as we will see in the last in the previous lecture, that what is the definition of negative vector. Now we will subtract both vector. Here is a vector A and vector B. This is same by using head to tail rule. The head of a vector A coincide the tail of vector B, and this is the resultant vector, that which is coinciding the tail of A and head of B. Here is some properties of a vector addition. We have to consider three vectors A, B and C. These are the properties of vector addition. First, A vector plus B vector, which is equal to B vector plus A vector. This is known as the commutative law, and geometrically we represented A plus B and B plus A. This is the law of parallelogram in geometrical representation. A plus B vector plus C vector, which is equal to A vector plus b plus c vector, which is the associative law of addition. Here is the additive identity and inverse identity with a vector a adding by the negative vector of a, which is the null vector, and additive identity of a vector is null vector. Here is some important points that according to all these properties, we know that the vector addition form an abelian group by using in the abstract algebra, a group theory. We know that if all the properties satisfied, then we say that the vector say that the set is abelian. Here we are using vectors, so vector is a abelian group. Here is the property. First property we will prove that, which is the law of parallelogram, by using the geometrical representation vector of a plus vector of b. Now here is vector a and vector b. This is the addition of vector a plus b, as in the previous slides we have been seen that how we are adding the vector by using head to tail rule. The head of a vector a coinciding the tail of vector b. This is the resultant. Now the right hand side can be added same. Here is a vector b parallel to this vector, which is a vector b, and adding the vector a. This is a left hand side a plus b, which is equal to a plus b, and this is the b plus a, which is the right hand side, and the resultant vector is same as we have seen. This is the law of parallelogram. The resultant is the diagonal of the parallelogram. Now analytically we consider two vectors a and b. A is equal to a1 I unit vector, a2 j unit vector plus a3 k unit vector, and b vector is equal to b1 I unit vector plus b2 j unit vector plus b3 k unit vector. Consider the left hand side a plus b, which is equal to, by substituting the value of a here and plus substituting the value of b. Now rearranging the values of a and b in component of I, j and k. A1 I unit vector and B1 I unit vector is here, which is the coefficient of vector I unit vector, and A2 and B2 are the coefficient of J unit vector in the form of sum, and A3 plus B3 are the coefficient of K unit vector. Now rearranging that, uh, a1 plus b1, which is equal to b1 plus a1, and a2 plus b2, which is equal to b2 plus a2, a3 plus b3, which is equal to b3 plus a3. Substituting the values same as we have been seeing that a plus b, which is equal to b plus a. The vector in here, all the component of the vector are first, then the vector b is first, and then the vector a is second, as we have been seen here that a is at second point, so a is here. Now the proof of the second, which is the law of associative law. For three vectors, consider three vectors a, b and c. Vector a is equal to a1i plus a2j plus a3k. Vector b is equal to b1i unit vector plus b2j unit vector plus b3k unit vector, and vector c is equal to c1i unit vector plus c2j unit vector plus c3k unit vector. By considering the left hand side, we give a name a plus b plus c, which is equal to another resultant vector d, substituting the values of a. Here is the value of a that we have been considered. Here is value of b, and here is the value of c. And by rearranging that, the all the first component are coefficient of I, so we arrange here a1, b1 and c1 coefficient of a. The second component of all three vectors is j coefficient, so we added here a2 plus b2 plus c2 j unit vector plus a3 plus b3 plus c3 k unit vector. Now we will have to see here geometrical proof as a vector plus, as see that in the left hand side that a plus b vector in the form of bracket, we added first a plus b vector by using head to tail rule. Next adding the vector c, this is the vector c. Now in the right hand side, vector b plus c, Here we add vector b and vector c, which is equal to b plus c. Both vectors have the same resultant vector d, which is equal to a plus b plus c and a plus b plus c. Now complete the analytical representation. Here is the analytical representation that a vector is separate and b and c vector are can be written in the form of this. This is a vector a plus b plus c, which is equal to right hand side. Now we will prove. Now we prove the third part of our property, which is the a unit vector plus null vector, which is equal to a, which is the additive identity. Consider here a vector a1 I unit vector plus a2j plus a3k, and null vector can be written as 0i plus 0j unit vector plus 0k by adding the same component a1 plus 0 into I, a2 plus 0 into j, a3 plus 0 into k unit vector, which is the same because we know that the 0 is a additive identity. So if we add the any value in their identity, we get the same term, which is equal to vector a and the right hand side. Here is we are lefting the fourth property, which is equal to vector a plus negative vector of b, which is equal to 0 vector. For the exercise, in the next video we will be discuss about the dot product and its characteristics and properties. If you do not subscribe our channel, then subscribe our channel. Thank you for watching this video.